Hello everyone! In this lesson, we'll discuss how to guide the FANUC robot to complete the motor assembling task through the vision system. This will not only improve assembling accuracy but also improve production efficiency. First of all, let's learn about the assembling of the motor. There is a set of workpieces, including 4 workpieces: base, motor, reducer, and flange. Before starting assembling, you need to manually put the base into the automated warehouse, putting the motor into the storage position of the rotary feeding module. Place the reducers and the flange workpiece randomly into the feeding bucket of the feeding module. The position of the flange at the end of the conveyor belt is flexed, but the angle and the posture of the workpiece is arbitrary. If the industrial robot grasps the flange with a fixed grasping position and posture, the flange may not be correctly assembled into the base. Therefore, there is a strict assembling requirement between the flange and the base. As shown in the figure, the flange fits correctly into the base. This picture shows that the flange doesn't fit into the base. In order to solve the problem that the flange can be correctly assembled to the base at any angle, we need to introduce vision to help the industrial robot position itself. Next, please answer this question. In the motor assembling process based on vision guidance, why is it necessary to introduce a vision system to help industrial robots position themselves? A. In order to increase the robot speed. B. To reduce manual intervention. C. To cope with the arbitrariness of the angle and the posture of the workpiece. D. To increase the load capacity of the robot. I will give you 5 seconds to think, and will show the answer after 5 seconds. The answer to this question is C. Did everyone choose the right answer? Next, let's learn the steps of vision-based workpiece positioning and grasping. Let's first look at the reference position offset method. Here, the vision-based workpiece positioning and grasping adopts the reference position offset method. That is, place the workpiece at a suitable position in the camera's field of view. The camera takes a picture to identify the position of the workpiece in the camera coordinate system, and the industrial robot teaches the grasping position of the workpiece, which is used as the reference position. For example, in this picture, directly above the flange is the Cognex smart camera. We manually place the flange and use this relatively correct angle as the reference. At this time, the angle is set to 0, and the x-coordinate of the flange center point is set to 0, and the y-coordinate is set to 0. Then, when the workpiece is randomly placed at any position, in the camera's field of view. The camera takes pictures to identify the position of the current workpiece and combines the relationship between the camera coordinate system and the industrial robot coordinate system. The grasping position of the current workpiece is obtained through position offset calculation, and the industrial robot grabs the current workpiece. The relationship between the camera coordinate system in the industrial robot vision sorting workstation and the industrial robot world coordinate system is shown in the figure. The positive direction of the x-axis of the camera coordinate system is parallel to but in the opposite direction to the positive direction of the y-axis of the industrial robot world coordinate system, and the positive direction of the y-axis of the camera coordinate system is parallel to and in the same direction to the positive direction of the x-axis of the industrial robot world coordinate system. Next, please answer this question. What is the relationship between the camera coordinate system and the industrial robot world coordinate system in the reference position offset method? A. The x-axis of the camera coordinate system is parallel to and in the same direction as the x-axis of the robot world coordinate system. B. The x-axis of the camera coordinate system is parallel to and in the same direction as the y-axis of the robot world coordinate system. C. The x-axis of the camera coordinate system is parallel to but in opposite directions to the y-axis of the robot world coordinate system. D. The y-axis of the camera coordinate system is parallel to but in the opposite direction to the y-axis of the robot world coordinate system. I will give you 5 seconds to think and will show the answer after 5 seconds. The answer to this question is C. Did everyone choose the right answer? Okay, let's keep going. Next, we verify the relationship between the robot coordinate system and the camera coordinate system through practical operations as shown in figures 2A to B. The workpiece only changes in one direction and the x-coordinate in the camera coordinate system decreases and the y-coordinate in the robot coordinate system increases, indicating that the x-coordinate system of the camera is parallel and opposite to the y-coordinate system of the robot. Place the workpiece at the reference position and use the camera to take pictures to identify the position of the workpiece in the camera coordinate system, and teaches the industrial robot to grasp the workpiece position P1 in the world coordinate system. When the workpiece is placed at any position and the camera's field of view, and the camera identifies the position of the workpiece in the camera coordinate system. By taking pictures, then the offset of the workpiece in the industrial robot world coordinate system and the offset in the camera coordinate system are shown in the figure. Combined with the relationship between the camera coordinate system and the industrial robot world coordinate system, the industrial robot grasping position P2 of the workpiece at any position can be calculated. Note, the workpiece position recognized by the camera is the coordinate pixel value in the camera coordinate system, which need to be multiplied by the ratio of the actual size to pixels to get the actual coordinate value. Next, let's study the concept of the ratio of actual size to pixels in detail. mm per pixel represents the ratio of the actual size of the workpiece to pixels, which means the ratio of the actual size of the workpiece to the pixels of the workpiece size obtained by the camera. For example, as shown in the figure, the value of circle diameter obtained by taking pictures with the camera is 316 pixels. If the actual size of the circle is 50 mm, then the ratio of the actual size of the workpiece to pixels is 50 to 316 equal to 0.15. Next, please answer this question. In practical operation, how to calculate the actual coordinate value of the workpiece in the camera coordinate system? A. Use pixel values directly. B. Multiply the pixel value by the ratio of actual size to pixels. C. Divide the pixel value by the actual size. D. Add the pixel value to the actual dimension. I will give 5 seconds to think and will show the answer after 5 seconds. The answer to this question is B. Did everyone choose the right answer? Okay, let's keep going. In the actual operation process, we need to manually place the flange first, as shown in the figure. Then, control the camera to take pictures. Record the angle of the workpiece. This angle is used as the reference angle. Then, operate the industrial robot to move to the workpiece grasping position and record the target point. This target point is used as the workpiece grasping reference point, as shown in the figure. An example of a program for position offset calculation is shown in the figure below. The vision-based workpiece angle compensation program is described below as an example program. The angle 1 is the reference angle. 基准点拾取法兰 is the grasping reference point for the flange. The angle 2 is the real-time angle of the workpiece. Next, please answer this question. In the position offset calculation program, how is the offset of the workpiece calculated in the robot world coordinate system? A. Use the offset value directly in the camera coordinate system. B. Multiply the offset value in camera coordinate system by the ratio of actual size to pixels. C. Add a constant to the offset value in the camera coordinate system. D. Divide the offset value in the camera coordinate system by a constant. I will give you 5 seconds to think and will show the answer after 5 seconds. The answer to this question is B. Did everyone choose the right answer? Everyone, in this lesson, we focused on the motor assembly and introduced the importance of incorporating vision system into the assembling process, as well as the specific implementation methods for the visual-based workpiece positioning and grabbing steps. The key points include position offset and angle compensation, and the calculation of the ratio between actual dimensions and the pixels. The content of this lesson is relatively difficult. Only if you review the content for multiple times can you fully understand them. That's all for this lesson. Thank you for watching.